Let's, as we as we said in the earlier closing remarks of the earlier lecture, when we get stuck in physics, well, its nature possibly offers us a solution. Well, first of all, my apologies for the fact that these J's should be subscripts. My PowerPoint again was acting up for whatever reason, but you are really clever guys and you understand what the J here means. It's a subscript. Well, the point is, so let us go back and knock at the first principles and search for uh, a novel solution if one exists, right. So, we discussed at length here in the previous lecture itself that D is epsilon naught E plus P, E is the applied field, P is the polarization, and P, the first order P, the linear part of P was epsilon naught chi, okay, and this is being multiplied by a vector P. We are writing this equation in terms of in a component wise form. So, therefore, the two vectors E and P can not only be mediated by a scalar in this equation, it can also be mediated by a second rank tensor if you wish. That second rank tensor is chi ij, and we discussed that we are, when we write the scalar equation, Pi is epsilon naught chi times Ej or Ei, whatever must be the case there. If we treat chi to be a scalar, then we are in the approximation where we are working in isotropic medium, which is not the most general of cases or conditions. First of all, here sum over j is implied. Okay. So, we are using the summation condition. So, Pi is epsilon naught chi 1 I j E j. Okay. So, sum over j is again implied in this case, right, but the matrix chi I j has 9 elements in general because we are in 3D space. So, j of course, I and j because we are in 3D space, I and j run over 1, 2 and 3. So, chi I j has 9 elements, out of which 6 are independent, and in the diagonal form we have 3 eigenvalues. We are allowed to write the scalar expression only in the case that the medium is isotropic, which is in which case in its diagonal form chi 1 1 would have chi 1 would have chi 1 1 1, chi 2 chi 1 2 2 and chi 1 3 3 to all be equal. This is the condition for isotropy. Okay. So, now we know from basic optics that since D is epsilon naught E plus P, P is epsilon naught chi 1 I j multiplying E j. Now, we substitute this into the equation, d I is epsilon naught 1 plus chi 1 I j E j plus and so this essentially lends itself again to another iconic equation, which is D is epsilon E. Again, earlier in elementary optics studies, we treated this to be a scalar, meaning isotropic media, which is not the most general case. In reality, we should treat this to be the appropriate second rank tensor epsilon ij, where epsilon ij is related to chi ij by the equation in the gray box, right. But we know the relationship between refractive index and the dielectric constant, okay, epsilon. So, but we already examined all this in terms of chi, so this is a bit of a repeat, but the point being that the refractive index, since our goal is to somehow, do not forget our goal is somehow find a way to make n at omega is equal to n at 2 omega possible, somehow make this possible. So, we are in the search for doing this, right. The problem was in normally or anomalously dispersive media, we are unable to do this when we basically have the k vectors of the two beams parallel in whatever sort of medium that is, right. Later on we will see that we may even be able to do it in a medium where the k vectors are indeed parallel, but what is the trick? That is the question we are trying to answer. Now, what do the indices I and j correspond to, okay, in terms of their direction? These indices I and j here correspond to the polarization of the electric field polarization of the beam involved in these media, okay. So, what does this tell us? All this tells us is that so far we looked at refractive index as something depending on the frequency of the driving electric field E of t. We did not consider its vectorial nature at all. Now, for the first time in this course, we are encountering the scenario where refractive index depends on the direction of polarization, or more specifically here linear polarization. So, this gives us an extra handle, an additional knob to tune refractive index, right. So, can we exploit this for realizing the holy grail, that is omega is equal to 2 omega? Can we exploit this? Let us see, that is the whole idea. Now, as I earlier pointed out, just as chi I j, and the rest of the discussion we will do in terms of epsilon I j, okay, keeping in mind that n, the refractive index, here the real part of the refractive index is square root of epsilon I j. So, you take element by element square root of the epsilon I j matrix, which is 3 by 3 and is entirely real valued. So, it is an R3 as we call it. So, basically this is a matrix, it is a 3 by 3 matrix in real 3 dimensional space, right. Essentially it has 9 elements, but we realize, or we earlier discussed the fact that epsilon I j is symmetric for these real cases, right. So, as a consequence, E21 is equal to E12, E31 is equal to E13, E32 is equal to E23, okay. So, therefore, you can say that the lower diagonal elements are equal to the upper diagonal elements in this matrix, right. So, therefore, the number of independent elements in a general orientation of things is reduced to 6 from 9, okay. So, furthermore, any symmetric second rank tensor can be transformed from its non-particular form to the principal axis form, where, as I said, you can diagonalize it. So, only the 3 eigenvalues remain on the diagonal of the matrix and the rest are all zeros. you study this in physics and engineering math. So, therefore, we only need to know 3 numbers to characterize any mediums epsilon ij, right. This is all this about the principal axis transformation, and how to do it is detailed in Professor Strang's very nice books and his iconic lectures on MIT OpenCourseWare. We basically use the Gram-Schmidt process to determine the eigenbasis for this second rank tensor. Of course, you must have learned this in an appropriate course dedicated to mathematics and linear algebra, or even otherwise perhaps. So, the standard trick is to do a principal axis transformation and figure out that this is a 3 by 3 matrix. In the 2 cross 2 world, I am just shown an example here. So, if this ellipse represents the second rank tensor, okay, the second rank tensor in 2 dimensions, how that is to be, again one studies that, but be that as it may, for the purposes of this course, it is sufficient to appreciate the fact that the physical quantity, which is having an elliptical geometry here and an ellipsoidal geometry in 3D space, can be transformed from any axis of choice, which is the black axis shown here, to a form wherein the entire ellipse is described by 2 numbers, its major and minor axes. So, that is what the principal axis transformation does. It is just a rotation in a space of appropriate dimensions. Okay. Now, there are 2 types of optical media, okay, and I refer to an excellent discussion on this in the book by Tyagarajan and Katak in called Optical Electronics, published by Cambridge University Press. The most general cases discussed there, and also Professor Tyagarajan's lectures on the same platform NPTEL. Please have a look at those for again a very scholarly discussion. Now, in the most general case, the epsilon tensor can be diagonalized so that it has 3 in general distinct eigenvalues epsilon 1 1, epsilon 2 2 and epsilon 3 3, and the off diagonal elements are zeros. So, in all such cases we must appreciate the fact that we cannot take isotropy for granted. There is no isotropy in general, or we in fact here want scenarios where isotropy is not happening. If isotropy happens, we would seldom be able to do any kind of phase matching, because the n omega and equals n at 2 omega condition can probably never be met, okay. Unless maybe epsilon becomes 0 or epsilon is near 0 or things like that, okay. Those are some exotic cases which I am not attempting to go into. That is an entirely different discussion, but in most media we will have to deal with the phase matching condition considering the restrictions and limitations and constraints imposed by nature. And if we do not have isotropy in a condensed phase medium, then what do we have? Then such media turn out to be crystals. So, we must consider crystalline media. In crystalline media, considering that the epsilon ij tensor can have 3 distinct values epsilon 1 1 2 2 and 3 3, if the any 2 components of the non-zero diagonal elements in this form of the tensor turn out to be equal, then such media are called uniaxial, meaning media possessing one axis of whatever, right. So, in these media, why are they called uniaxial media? In these media, there is one axis of rotation, okay, about which when rotated the medium remains invariant. Okay. So, the whole point being that there is some special direction. Let us label this as z. If this is z, then obviously you have an x and y somewhere, and a block of the crystal of this uniaxial medium, when rotated about this special axis, okay, it seems does not undergo any change, well, optically speaking, that is to say. Okay. So, in this case Exx is equal to Eyy. So, what does this actually mean? This essentially means that if a wave with a propagation vector k along this direction traversed and it is linearly polarized, because the propagation vector is along the z axis or z axis, it is k times z hat. No matter in which direction the polar electric field is polarized on the xy plane, this owing to the symmetry of the uniaxial medium, right, the refractive index is going to be independent of the angle that the electric field vector makes with respect to either the x or the y axis. Okay. So, that is the uniaxial case. Now, there is a bit of an irony here. It so happens that if we have a medium where neither pair is equal, neither is E1 equal to E2 nor is E11 equal to E22 or E22 equal to E33. This is the most unsymmetric situation. There is no symmetry, it seems, in such a medium. Here there is some symmetry, E11 being equal to E22. In the medium where neither of these two are equal, you can find two such axes about which if you rotate, right, the system remains optically sort of invariant. Therefore, media where we do not have any equality among the eigenvalues or eigencomponents of epsilon are said to be biaxial media. We are not going to go into biaxial media in this course, it makes life complicated in practice, and also when there is, if you can achieve, we can achieve something with uniaxial media, we would probably want to stick with that. So, that is what we are going to do. Okay. Now, in uniaxial media once again I emphasize, where a pair of the triplet of the components of the epsilon tensor, the pair E11 is equal to E22, which is not equal to E33. That is very important. The not equal is equally or very important, right. Then such media have two distinct refractive indices which depend on the direction of polarization of light. Okay. From in this discussion, when I say refractive index, I mean only the real part of the refractive index. Okay. So, there are two refractive indices, say n something, n sub 1, n sub 2, which are not equal to each other. for all frequencies. And 1 and 2 depend upon what? Not only the frequency of not only the frequency, but also the direction of polarization of the electric field. Now, if we have a uniaxial medium, okay, maybe I should call this n sub 3 and not n sub 2, because we are going to make n1 and n2 equal. Okay. Now, be that as it may, if we choose a uniaxial medium, orient the reference axis so that the n corresponding to the polarization of the electric field along x and the polarization of the electric field along y are both equal, then this is equal to one particular value. We call this refractive index the ordinary refractive index. Whereas NZ is called the extra ordinary refractive index. This is NO, this is NE. Now, for linearly polarized wave propagating along Z can only have its electric field vector in the xy plane. Yes, the linearly polarized electromagnetic wave with propagating along the z direction can only have an electric field vector throughout such that only the x and y components of the field are non-zero. So, a wave that is propagating in the z direction, its refractive index is not going to change no matter in which direction of the xy plane the electric field points. So, this is instance 1, this is instance 2, let me keep the magnitudes or lengths of the vector equal. For all these orientations of the direction of the electric field, the wave is essentially going to have experience the same, see the same refractive index, which is NO. Again, when I say refractive index, I mean the real part of the refractive index. Okay. So, now this particular direction is a symmetry direction, and this direction is called the optic axis of the crystal. When light propagates along the optic axis of the crystal, the refractive index experienced by the linearly polarized electromagnetic wave is independent of the polarization direction of the electric field. Is the point clear? This is the way we look at uniaxial media. Okay. However, if an electromagnetic wave is propagates or enters a crystal at an angle and enters a crystal and propagates at an angle theta with respect to the optic axis, then the refractive index as seen by that wave, provided the electromagnetic wave is linearly polarized, is given by this equation. It is a complicated looking expression, but we will get used to it. That is 1 divided by the square of n. Now, n, remember, all this is happening at a single frequency, some single frequency omega. All this is happening at frequency omega. So, no frequency dependence arguments are going to present themselves. They are going to be dependent on the angle now that the k vector makes with respect to the optic axis. I am not even going to talk about polarization, the direction of linear polarization. I am simply going to talk about the angle that the k vector of my beam makes with respect to the special direction called the optic axis in the crystal. The optic axis is a direction. It is not a specific OX, OY or OZ axis or OZ axis. It is a direction in a crystal. Like north, the direction north points in the same direction irrespective of where we are located. The direction south also points in the same direction irrespective of where I am located anywhere, okay, on this planet, right. Likewise, east and west and whatever. So, you got the point. Optic axis is a direction. Now, if the propagation vector of the propagating wave of interest which belongs to a linearly polarized electromagnetic wave has a direction theta with respect to the optic axis, then the refractive index as seen by that beam n of theta can be written in terms of NO, the ordinary refractive index, and NE, the extraordinary refractive index, as 1 by the square of n of theta is cos squared theta divided by NO square plus sin squared theta divided by NE square. You can derive this from first principles, but you have enough knowledge on your plate to do this, but we are not going to attempt to do that explicitly in this lecture or this course. I once again refer you to Optical Electronics by Tyagarajan and Ghatak or Professor Tyagarajan's scholarly lectures on NPTEL. Okay. So, now I hope you are beginning to appreciate the following, that we wanted to, what are we trying to do? We want to achieve the phase matching condition which is still under question. N of omega at n is equal to n of 2 omega. Earlier, our problem was that refractive index monotonically increased with frequency for normal dispersion. So, this was seldom possible. But now maybe let us see if that works out, right. So, now the direction of the special direction that we said called the optic axis defines a symmetry axis for the case of uniaxial media, and n of theta relates to the two key refractive indices NO and NE through this equation, cosine square of theta divided by the square of NO plus the sine square of theta divided by the square of NE is n of theta, right. So, look at this equation, you can set a condition where the cosine of theta goes to 0 by having the propagation vector k at an angle 90 degrees to the optic axis, then n of theta is equal to NE, whereas if it is parallel to the k vector of the beam is parallel to the optic axis, then n of theta or n is equal to NO. So, we have a way to tune the refractive index of relevance to the beam by tuning the propagation vector in this case, or equivalently the direction of linear polarization of the wave in the crystal, right. We can plot this very nicely, okay, we can plot this very nicely. So, for any crystal, any uniaxial crystal, this is the plot that you want to keep in your mind, this chart, all right, this chart is what you want to keep in your mind. This plot of refractive index, okay, where the vertical z axis here this is the reference axis for theta is equal to 0, or we can call this the z axis by some convention which we always love to use. This is called the optic axis. Now, the term optic axis, I must just like qualify this for a bit, right. So, we are working in optics. So, therefore, we would always encounter scenarios. So, this is the theta is okay, right. This is the theta is equal to 0 line. We could use terms like optical axis of a system, that is also prevalent in optics and photonics literature. That is a little unfortunate, because in the case of birefringent media, okay, the phenomenon we are discussing here is called birefringence, that is the dependence of refractive index on the direction of polarization of a linearly polarized electromagnetic wave in a medium. The term optic axis is reserved for usage in the context of birefringent media or crystal optics, as it is sometimes called, whereas optical axis is a more general thing. In ray optics, you sometimes call it the system optics though, or even the optical axis, right. But please pay attention to how we spell it out here. In other words, in this context of birefringent media, please do not use the term optical axis, although one would possibly be able to figure out what you mean. That is not quite the technical or pedagogic term. So, OA is optic axis, the symmetry axis by propagating along which the refractive index is independent of the direction of polarization of the electromagnetic wave, which is linearly polarized. Now, the point being that this particular value n of theta for a beam propagating with a propagation vector k along such a direction, okay, if I plot this on an axis, this is the equation of an ellipse, you see, cosine square plus sine square divided by two quantities. So, these two determine the intercepts of the n of theta curve of this ellipse, right, whereas NO is independent of theta, right. We can perceive such a thing, right. N of theta is following a sort of elliptical trajectory in this space,